Anthony, if you stood on this side of me and Holly, you stood on here and you started like pushing at me, I'd just go,
we're going, this is weird.
This is weird. Musical theatre.
Yeah.
If you pushed, I would go and I would turn so that I was in a more comfortable position so that you weren't going to keep squeezing me and hurting my arms.
Welcome to Wonder, brought to you by Geo Co. I'm Holly Cooke, joined as always by my colleague Dr. Anthony Reid. And today we are sitting across from Dr. Sandra McLaren, former university academic, all-round just legend of a geologist. My superstar, my brain is absolutely flying. We basically track ourselves back to the early Earth, exploring why heat makes the world go round, the mystery of continents, what makes the world look like the way it is today. Anthony, I can't wait to get into this conversation. Thanks for coming on board, Sandra.
Thanks very much, Holly and Anthony. I can't wait to have our chat.
One of the great things about being a geologist, or being a person maybe even in general, is going outside and having a look at things, right? And one of the things that you see in the world when you go to natural places is that some places are hilly and some places are flat. Some places are, are deep and some places are, really high. So if you go from something as extreme as Mount Everest, eight or so kilometres above the Earth's surface, and some of those trenches in the Pacific go down, 10, maybe 12 kilometres? They're pretty deep. So why is that? Why isn't it just...
We have another why for you.
Have another why.
Why isn't it just flat?
Oh, it's such a fantastic question, and it draws exactly from our observations that we can make. We do travel places, and even if we don't get to travel very far, and some people aren't able to travel very far, you can still see such vast differences in the landscape around us, and that is all geology. That all comes down to geology, and it comes down to a thing that we call tectonics, which I'd like to talk about.
Oh, please.
Okay. Please. Tectonics are so cool. So the fact that we have differences in elevation, which we can give the fancy name to, it's a hypsometric curve. Which
wow,
is
that is a pretty fancy name. I don't know if I can spell that.
Not good, not great for crosswords, that one.
That would be worth a lot in Scrabble, though. Surely.
Oh, true, yeah,
Sure.
wise, yeah.
Anyway.
So this is a way in which we map and see how much of the land of the Earth is above sea level and how much is below, and then which bits are at which level. So we can map that out, and we can see quite easily that there's a big range, as you say, from the top of the Himalayas to the bottom of the trenches in the Western Pacific, and lots in between. And the only reason that we get that kind of distribution is because we have active tectonics still on planet Earth, and that relates to how the insides of the Earth are operating, and particularly their thermal story, which we've talked about before. So if we didn't have active tectonics, we would still have rain and stuff happening, and that would gradually erode the mountains down, and we'd end up with everything being flat and
basically
boring.
Flat.
Yeah, good for your fuel economy in your car.
Terrible for the scenic walks.
Exactly. Terrible for the tourist bureaus. They would not like it at all. Everything would be flat.
Because it's right? Because rainfall has been happening since whenever the atmosphere had enough water to dump it out as a rain shower. Glaciers have been happening for billions of years as well, and it should have done their job by now, because that's their job, right? To scrape stuff off the top and dump it down somewhere else.
Exactly, to even it out, to basically plane it off. And it's doing that job, but at the same time, the land is just going, I don't like you. I'm going to just pop up a little bit more. So you've got a little bit more to wash off and to grind down. And there's a couple of key processes that are behind that. First of all, the one we already mentioned is tectonics, and the other one is isostasy, which is another fabulous word for crosswords. And that refers to the way in which if you cut off a bit of the land, in order to maintain the density, it just gradually rises like a wooden block in a bath. So as the rain falls on the Himalayas and washes the stuff down onto the plains, the mountains just pop up a little bit more and say, ha ha.
So if you sprinkled some creative license on that, you could say that the rain carving away big mountain ranges actually helps them grow, because the Earth's bottom needs to pop it back up to maintain some kind of equilibrium. Exactly
that, Holly. And what happens when we produce something like the Himalayas, which is this process tectonics that we'll talk about? So we have the upper bit of the Earth, which is the crust and the solid part of the mantle. So we've talked about the mantle before.
It's not liquid.
No, it is definitely not liquid, never liquid. No, that's not true. Sometimes some bits are, but no, on the whole it's not. So it's solid, but it can move around, convect if it's hot enough. But you have to go down about 125 kilometres straight down before those mantle rocks, the olivine-dominated rocks, are hot enough to move around. Everything above 125 kilometres, which is quite, significant distance.
That's decent.
Yeah, exactly. Straight down is solid. So that's just a thick lid. So the crust is a little bit, and then the mantle lithosphere. And that just gradually gets shunted around because the mantle underneath, which is hot, is convecting. And so there's ways so that will just gradually move along, but eventually it's going to crash into
something.
And as you keep pushing it and it keeps pulling itself, you have the capacity to build these really big mountains. And so when we have something like the Himalayas, which is 8-9 kilometers high, it actually has a root. So a bit like a foundation of your house. So the lithosphere is thickened there to about the crust is thickened to about 70 kilometers. So we have a lot more material there.
What we just did there is we had a conversation with Sandra about heat making the world go round. We said big words like mantle convection, and now we're figuring out that we've got these plates. We call them plates that sit on top of everything, and it's a bit of the mantle and it's all of the crust, and they sort of dance around the planet.
Exactly.
And that's what makes the mountains. Because I remember thinking, what about heat? What's the heat? Why does heat make mountains? It's the plates.
Exactly, Holly. It's exactly right. And if you just think about being at a campfire or even at home with your stove and you've got some water boiling and you might want to put in, I don't know, something, even like a spinach leaf or something or other that's on there and it's a raft, and you can see that there's a hotter spot in your stove, and so water bubbles up. And if you've got something sitting on top, bit of carrot, bit of lettuce, whatever it is, it will move away from that, and then it might get caught up in another hot upwelling and it will move in a different direction. And so all over the earth, we've got that happening. So the plates, so that, as you said, the crust and the upper part of the mantle are moving around and interacting with one another. There's no gaps. There's no hole.
Yeah.
The plates are always up against one another, but some are moving this way, some are moving that way, some are colliding, some are both moving this way, but this one's faster, so it's going to crash into it.
So what's some examples of plates?
Lots of
that people will know.
Yeah, so Australia's very special, very lucky country, of course, but we're also very lucky in that we have our own plate all to ourselves. And many countries actually have, parts of multiple plate. But
so they have the joins of different plates inside different areas.
Complicated places.
Where's a complicated place then?
Places like Japan, Iceland is extremely complicated. Most of the countries in Southeast Asia are really complicated as well. Africa's another simple-ish place. North America is a little bit complicated, but not that much, but only on a sort of north and south. But Australia, the continent, sits on its own plate, and it runs all the way from the bottom end of New Zealand up to the Himalaya nearly. So it's it's a jelly bean sort of shaped plate. Mm-hmm. Plates can be all sorts of different shapes and sizes. The biggest one is the Pacific plate. So most of the Pacific Ocean that we know is a single plate, and it interacts with plates that are more continent dominated, like North America, South America, Asia, at the edges, which many people may have heard of as being the Ring of Fire. That's the edge, the plate boundary between the Pacific plate, which is huge, and the plates on either side of it.
So plate boundaries are pretty important places for geology to happen?
Absolutely. That's where the action is happening today that we can see and feel and experience as
Could we see and feel?
This bad boy. Obviously I've got a rock collection at home, and this is, it's so heavy. I was just saying, carrying it to here was such an effort, but this was from a trip that I did in New Zealand, and it was taken at the plate boundary between, oh my God, I'm going to actually mess this up. It was the Australian plate and the Pacific plate. Yeah. Beautiful. And it's basically where they're smashing up against each other and building the Southern Alps of New Zealand. And this is the kind of heavy rock that comes about from it.
That's a fabulous rock. And we do get different types of rock forming in exactly those scenarios, because that's where the rocks are forced to be changed.
Like interact in some way?
They can interact with one another, and they can also just be modified in and of themselves, because if, like, Anthony, if you stood on this side of me and Holly, you stood on here and you started pushing at me, I'd just go,
we're going, this is weird.
This is weird. Musical theatre. Yeah. If you pushed, I would go and I would turn so that I was in a more comfortable position, so that you weren't going to keep squeezing me and hurting my arms.
Yeah.
And that's what rocks do, and that's rock deformation. And that happens where the stress is really high, so you guys are pushing on me, and which relates to what's happening at the plates. And the rocks can undergo all sorts of changes in the mineralogy, like what minerals are in there, changes in the texture, which is what your rock is showing, Holly, which is beautiful. That's what we call a proto-myelinitic texture, which is where you actually squeeze the rock so hard, you grind most of it up and smear it out into really long layers. And sometimes you end up with a really strong bit that gets left in the middle, and you have a few of those in there, which are feldspars. Yeah. And this happens where we interact the plates and the stress is higher and the rocks are weaker, so they're more likely to do this.
Oh my God, I love this. There's one of my favourite books is by I think you pronounce her name Marcia Bornurud, and it's called Timefulness. And in it, she has this passage, and it's obvious to geologists, but it's worth saying again that rocks are evidence of processes.
Absolutely.
They're not nouns, they're verbs.
Yes.
And so at that plate boundary, like I was smacking that, like, oh, this is amazing, because it's sort of like putting your hand on something which is an earth maker. It's a process which makes the earth, and there's something just like, I'm just a human. This is so much bigger than me.
Absolutely, exactly right. And it's so special to be able to put your hand on a plate boundary like that. I've only ever done it once or twice. It's not that common, at least for us growing up in Australia. I mean, it is in many other countries of the world, of course, who have to deal with the difficult consequences of plate boundaries, which is this deformation is happening, as we've talked about, to the rocks, but on a day-to-day level that manifests as volcanic activity, earthquakes, and things that are very quite hazardous and damaging for people, which is really hard to reconcile that.
Well, I was just about to say, the countries a couple minutes ago we were talking about where are the complicated, like where are some of the nexus of some of where these plates meet. And we mentioned things like Japan, Iceland, and all that was going through my mind is these are places that are quite ravaged by natural disasters like earthquakes. We've got Iceland erupting, and, you know, where we have these big earth activities like eruptions and earthquakes, that is where the plates are doing their doing their work.
Yeah, that is the day-to-day human scale, because we've talked about before, and you've spoken about before. Most of geology is kind of slow, laid back, happens pretty quietly, pretty slowly. We can't see it as humans on a human timescale, but where we have the plates interacting, we get these events happening and the rocks undergoing the change. So we do get the dramatic earth activity that we see manifest in earthquakes and volcanoes and other associated hazards.
So without earthquakes, mountains wouldn't grow?
Exactly, yes. So mountains grow as a consequence of the accumulation of lots of different earthquakes. So an earthquake is when you've got two rocks together and they're push, and then a break forms, so a fracture forms, and then one lot of rocks suddenly goes like this and moves on the other one. And that change of kinetic energy will actually make the ground shake, and that's what you feel as an earthquake. So over millions of years, you need to build up something like the Himalaya on multiple hundreds of millions of different individual earthquakes, moving the rock a little bit more, gradually building it up. Exactly.
So is it like there's got to be incremental build-up of many little faults?
Exactly.
Movement on many faults will lead to something as big as that.
Exactly. And so you can sort of imagine, there's been some recent earthquakes in the news, and you might have seen pictures of a big fracture in the ground, or a little bit of a scarp where a bit of the ground's gone up and you can actually see it, and it might be 1 or 2 meters at most. And you imagine how many of those you need to build up incrementally to build up 8 kilometers of the Himalaya. And then as a geologist,
So what, sorry, Sandra, you were about to say, but my question immediately then was, why don't the plates stop?
Mm-hmm. Yeah.
Like why does that keep happening? Because you would think that that's a lot of pressure. That's a lot of kind of stress. Thank you. Stress is the key word. Stress. A lot of stress pushing on each other. So why doesn't it even out?
Yeah, that's a really good question, Anthony. And people have wondered that. People wonder, when did it start? When did these plates start moving around in this way? And why doesn't it just stop? And it's certainly true that some plate margins lock temporarily.
Right.
And so there's sort of nothing happens.
They're sort of almost fused.
Almost, but not quite. So there's a bit of debate about, I mentioned before about Australia sitting on this jelly bean shaped plate. And if you look at a bathymetric image, there's a near north-south line of things, which people have in the past argued whether that is a fused plate boundary.
Oh, this is in the middle of the Indian Ocean.
That's right.
Yeah, get on your Google Earth and look at where Australia is and where India is, and visualise that those things are actually connected on one enormous
plate.
I'll do it. Exactly. You've got me an excuse to go on Google Earth.
I love Google Earth.
Google Earth is the best.
It's really hard to.
Good.
Well, that's our evidence. You want evidence that there's a reason why oceans are created and mountains are made. Go look at some suspicious lines
Yes, exactly.
And zoom in.
Yeah, exactly. A fantastic suggestion, Holly, because when these things happen, they tend to happen in linear belts, and most of the rest of the plate, nothing happens. It just sort of carries along behind. Doesn't mean they're not stressed, though, because
is this what you're talking about?
Yes, that's exactly what I'm talking about. So sorry, I've digressed anyway to talk about fusion of plates. But yes, there's a suggestion that sometimes plates will have stuck together for whatever reason, and then new plates can start breaking. You break up an old plate and divide it into two. But yeah, why doesn't it stop? That is the big question. And that relates 100% to what's happening more in the interior of the Earth, where we've got the heat that's still trying to get out. And
It's all heat.
Everything's to do with thermal structure or the heat that we have within the Earth. So most of the heat, the most efficient way for the heat to get out is by movement of magma, so molten rocks via convection. So what happens at Iceland, what happens on the Pacific Rim, and that physically takes some heat out and it gets lost. So most of the heat's lost around the edges of the plates. But that's not very efficient, really, when you think of how big the plates are.
Think of all that, just picturing the heat building up underneath, like Eurasia, this enormous landmass, or the entirety of Africa or North America. They must be sitting on almost like a lid on top of a boiler plate, right?
Exactly. That's exactly a really good analogy. And that's so not much heat is getting out through these plate margins. So over the Earth's geological history, we've lost heat in this way, but it's still there. It's still trying to get out. So the plates are always going to keep moving as long as there's thermal gradient or heat inside that is trying to escape. So and over time, that's going to slowly, and eventually, no need to panic. In who knows how many billions of years, we would have lost all that heat, and the plates will move more slowly, and eventually they will all stop.
All right, I've got something really far-fetched to think about here. So as a kid, I was disproportionately worried about the sun blowing up, like the end of humanity being the sun, taking us over. Like I was a stressed out 8-year-old. But now I'm thinking, like, actually,
I hadn't even thought of this.
The monsters are actually closer because as soon as the Earth loses its heat, sort of the dance of our tectonic plates grinds to a halt, and it's actually this active Earth which I think supports life.
Exactly, it does. And a lot of the new nutrients we need for farming and things come from the enriched soils that pop up with the plate margins and things. So, yeah, absolutely. You're right. You were right to worry.
Now I'm a stressed out 23-year-old.
Yeah. You're just ahead of your time. You don't need to worry about it yet.
A few billion years.
All right. So we mentioned where these plates come together. So they're driven by thermal gradients, by heat trying to escape the Earth. The mantle is convecting these plates around the place, and where the plates come together is where the magic happens, and where the disasters can happen for societies living close to these plate boundaries. But what happens? What's the menu of possibility when you go on Google Earth and you see these lines? What's the menu of possibility of where these plates meet? What happens?
Yeah, that's a fantastic question, Holly, because there are quite a range of possibilities as to what can happen when two plates interact, and that what will happen will depend on which way they're headed, which in part is to do with what's happening in that convecting mantle, but is in part to do with what's happening elsewhere on that plate as well, whether it's being pushed from another side or pulled. So the direction of movement of the plate is the sort of number one controller, but there's lots of controls on that. And then it's the direction and the rate, how fast that's happening. So if you've got two plates that are effectively pushing into one another, you can, if one is denser than the other, it might go and actually start to go, no, don't want this anymore. I'm heavy, dipping. I'm hot, I'm tired, I'm going down.
It's late.
Yes, it's late. So I'm off.
Back to the mantle.
Yeah, exactly. And can dive down in a process that we call subduction. So that can happen whether we have a continent here or whether we have ocean on both sides or one of the other. And which way it goes can flip over time, which is always so cool that can happen. And that's what happened, what we think happened north of Australia when Papua New Guinea started to form. We had a flip of subduction. So it can dive down there. And the thing about that is once it starts to go down, it is denser and it just keeps dragging the plate behind it like this. And it kind of just keeps going. And
brings the whole a whole plate with it that's just all going down.
Exactly. And by pulling it there, over here somewhere, that gives a bit of a path of least resistance for the mantle to start popping up there, and that can start to drive that as well.
Like blue tack or Play-Doh. I'm holding like a bunch of Play-Doh and I'm pulling it on this side. It actually gets thin.
Yes.
It gets thin elsewhere. It has to thin.
Exactly. And so that might be where the mantle goes, oh, I can see a path.
I can pop up.
Yeah. And then you might get a new islands forming there because you've got volcanoes, and then you might start a different type of like earth, like life story for that plate from doing that. So that's one possibility. Another possibility is that both of the plates are pretty buoyant materials, so they don't want to go down. They want to go up. So they will just start to crumple, and we'll start to build up our mountain up the top here. So this is how we have the Himalayas. That was the continent of what's now India and Asia, just bearing, and they both said, I'm not going down. I'm not going down.
We both go up.
Exactly. So we both go up.
Headstrong.
Yes. So we build up a thickened zone at that plate margin. So that's another option. Another option, of course, is if the plates are actually going apart from one another. So, which is kind of what you said.
We need to go our separate ways here.
Exactly.
This is not working for me.
Yeah.
Enough for you.
I've been with you for billions of years now.
Tired. I need a change.
That's
exactly. So this is what's happening in Africa at the moment, and also through the middle of the Atlantic Ocean, where we have plates moving apart. And the effect of that, of course, is that the mantle again goes
up.
Place for me, up I come. And we build volcanic chains along that as well. So there's an extension or margin. And then the third possibility is that the plates are just like, oh yeah, bye.
Hey,
and it's just,
bye and bye.
Exactly, just sliding past one another like,
ships in the night.
Exactly.
So let's name some examples. I think of the movies. Is there a movie called San Andreas? Or is there like a big disaster movie on the transform fault slipping through? So we've got like these...
Bad person to ask.
I know, right. Moving right on then. So we've got these like slippy... They're just chilling, moving past each other. You still get earthquakes. And then we have the big Himalayas where the plates don't want to go down. Instead, they're going, all right, we're all going up together. And then right back to the first example, which is when one dips and goes, no, I'm out of here, I'm going down. Would that be the bottom of Mariana's Trench kind of thing?
Absolutely, Holly, that's right. And one of the reasons why that's so deep is that's the oldest part of the Pacific plate. So we said before how big and when you look at Google Earth,
it's huge.
It is humongous. And that is some of the oldest material. And when it's older, it's colder and it's denser because it's been around for long. So it's more likely to go steeply down. So the Marianas Trench is one of these subduction zones, absolutely. But there's plenty of them. They're all the way through Tonga. If you have a look at Google Earth as well around Tonga, that's a very deep trench, but same thing, old oceanic crust of the Pacific plate diving under the Indo-Australian plate, and you form these huge big trenches and they just sort of roll along. Yeah.
All right. Would you like to ask a question?
So what I started thinking about when you were explaining that is I think we have to explain a little bit the fact that you have continents, and we talk about oceans, but we don't mean the watery bit, right?
No, we
don't. So what's the difference between a continent and ocean?
Yeah, and a really good point, Anthony, because we do bandy those words around, and we don't mean the water at all. It'd be easier if the water wasn't there because we get to see
we get to see the real ocean.
Exactly.
These oceans
come to Mars.
Yeah, the geoscientist version of when we talk about the ocean is who cares about the water?
Exactly.
It's the rocks.
Terrible, isn't it?
Don't
tell the biologists.
So oceanic rocks.
Exactly, oceanic rocks. So they're very we've talked in the past about the difference in composition between crust, mantle, and core.
So like chemistry, right?
Chemistry, exactly, what they're made up of. But there's a huge difference between continental crust and oceanic crust. So these, and again, relates to the melt bust that I talked to you about last time.
Yeah.
Because different materials are going to come up and stay up, whereas other materials are going to get processed more efficiently. So the uranium and thorium and potassium that catch that melt bus are buoyant. They tend to be in buoyant rocks, so they'll sit up longer in the earth, and they form the continents. And how continents formed and when the first continents formed, we still have arguments about in the geological community. We still don't, and I still conceptually, sometimes I lay awake at night and I think, but how do the continents start? Like, how does it start?
Great question. Yeah.
Oceans are much easier to understand, but continents are much more engaging question, but so much more difficult to answer. But the oceanic crust is the material is obviously below the sea, and we get to see it in places like Hawaii, Iceland, so on. We get to see samples of it. Is melt from a much simpler source. So just from the mantle as it is today, you melt that and you just get basically ocean crust that we get now that's being produced in these volcanoes at sea. And it's all the same. And that tells us something pretty important as well, because it's telling us that it's come from the same stuff, and that same stuff has been the same for at least 250 million years, so deeper down in the earth. Because if you're making a cake, let's get back to some food, and you just throw all your things in there and just melt it once, and then you were to come along and, get a teaspoon out, you might get a bit of flour in one go, you might get a bit of sugar.
Mixed.
Exactly. You might get the raw eggy stuff.
Eggshells in my case.
But if you mix every time you come along with your spoon, you're going to get basically the same stuff. So we can extend that to what's happening in the oceans. And so when we built the continents, we're basically getting unmixed stuff or from a different source. But when we got the oceans, we're just getting the same boring stuff. I didn't say that.
Let's go hard at this. I've heard the first mystery of continents is just an awesomely horrible question, which is like, when did continents start? What are the first continents? What's a continent? What is a continent? If we're still hovering in outer space, looking at Australia, Eurasia, whatever, what do we call a continent?
Yeah, good continent, because continental crust can be below the sea. So
stop it.
It's complicated.
It's complicated. So what we see looking from space is we see what we find on a map today, and we see the bits of the continent that are above sea level. But there's a lot of it, you may have heard, continental shelf, which is where the continent keeps going under the sea, and eventually usually grades into the oceanic crust at a continental margin. So I've spent years when I was an undergraduate student, still couldn't get my head around where the continent stopped and where the ocean stopped. But pretty much most plates have at least some continental crust and some oceanic crust. And they're usually gently next to one another. There's not like a massive line or a mountain range or something. Sometimes there is, but often it's a very gradual transition. It's what we call a passive margin. And so Australia, we have the continent of Australia, but it goes all the way up into Papua New Guinea because we collided with them, and our continent's, saying this is my spot now. And if you have a look at the shelf, it extends quite a long way. And then people have recently discovered the Zealandia, which you may have heard about, being this sunken, submerged continental fragment that ties in with New Zealand. So the water kind of does get in the way when you're trying to understand the differences with the rocks. Yeah.
Totally. Well, I reckon it would be amazing to touch on this. You've spent plenty of time in Papua New Guinea, which is just, oh goodness, I'm not going to try and explain it, but can we talk about how is Papua New Guinea actually secretly related to Australia and related to the tectonic conversation?
Please.
Yeah, it's an amazing place, just absolutely beautiful, and an amazing place geologically and culturally as well, of course. But half of it's kind of Australian in the sense of a geological sense. And so what was happening is Australia was once next to Antarctica, as you might know, and then started to spread apart pretty quick, 7 centimetres or so a year, rocketing north. I'm out of here. And then it eventually started to interact with various very, very complicated set of small plates we call microplates that are in Southeast Asia. So this is the process that started to build Papua New Guinea up. So some bits of Papua New Guinea are much older, and you can see what they were originally an arc, which is a type of island where we get melt of the mantle when you pop up a nice little island. And there's it's like a patchwork, it's like a jigsaw puzzle where someone's raided your cupboard and taken out like 4 or 5 pieces from each puzzle and stuck them together. And that's a nice analogy for geology and the process of tectonics anyway, is that you can like Velcro different bits together. So Australia was just hammer barging up and started to butt into these little islands that had previously been there. And there's some continental material there, so it won't go down. So it sticks together and starts to build the mountain range. And it's an incredibly beautiful mountain range. I've not been up to the highlands, but 4 or 5 kilometres up. So it's quite
substantial.
Yeah, and to be right on Australia's doorstep, and yet and Australian rocks, about halfway through the country of Papua New Guinea, you can draw a line and say this is originally Australian continental crust, and this is original Pacific continental crust. But it's an amalgam of lots of different bits there. And it's even today, we mentioned before about how these plates move around. We can measure that really well now because we've got GPS and other satellite technologies. And you can map where the different bits of PNG are going. And it's just like someone's dropped a series of, arrows in different directions because they're all remnants of really complicated past histories that are now stuck together, forming this new continental block. So.
Incredible. The story of continents.
Yep. Amazing. Yeah.
Fantastic. This is like, you've had a good conversation when my head's exploding with questions and thoughts still. Like I feel.
I know. We could keep going for a long time here, but please come back.
Oh, I'd love to.
We'll
Thank you
be
for having
dragging
me.
back here.
Yeah.
No.
Thank you very much for having me.
Thank you, Sandra.
Thank you.
For exploring, I think, what is just an absolute mosaic of oceans, continents, and the Earth colliding, pulling itself apart. Thanks for stepping us through it because it's a complicated thing. Hey.
Yeah. Thanks, Holly.
Cheers.
Thanks, Anthony.